Welcome back. In the last video, we looked at simple linear regression, which uses one predictor. In this video, we'll look at multiple linear regression, where multiple predictors are used to build a model. I've opened Notebook 5.2. We're looking at another built-in data set, chick weight. We can find out more about this data set by typing $chick weight at the console. And we see it has 578 rows and 4 columns. The data was collected from an experiment of the effect of diet on growth in chicks. So we have weight, time, there's a number indicating each individual chicken, and diet, which is a factor of 4 levels. Over here, I've used the dim function to find the dimensions of the data frame, and then looked at the first 3 rows. The weight is in grams according to our documentation. Let's look at a graph of the data. I've set the graphical parameters to be a 1x2 grid so I can show 2 plots side by side. The first plot is a scatter plot with time, which is days, on the x-axis and weight on the y-axis. And notice we have this funnel shape in the data. So every chick starts off at relatively similar weights, and as the days go on, their weights diverge quite a bit. I don't know much about chickens, so maybe that's not surprising. I know that people start off weighing about 7 pounds and end up weighing very different amounts at adulthood, depending on if they're male or female, their genetics, their lifestyle, and so forth. The second plot plots the diet. There's 4 different diets on the x-axis and the weight on the y-axis, and we get a box plot here. So it looks like diets 3 and 4 resulted in larger weights for the chickens. Next, we look at dividing the data into train and test sets. We can do that with this code block here. I set a seed for reproducibility so that every time I run this notebook, I get the same train set and test set. We use the built-in sample function, which is going to sample from 1 to the number of rows, which in this case is 578. So it's going to sample 75% of those numbers from 1 to 578 without replacement. And that will create a vector I, which is going to be a vector of indices. We can see that in the environment after we run it. I is just a vector of indices. So we're going to select using that index I. All of those are going to be in the train set. And then we have the syntax minus I. So those are all of the rows that don't have one of those indices. Those go into our test set. We'll end up with 75% of the rows in train and 25% in test. Let's build first a simple linear model, modeling weight as a function of time. So again, that's weight tilde time. And let's also do the summary. Looking at our residuals, we see that there's quite a range from -128 to +160 almost. And again, we don't care about the intercept. We want to look at the time, our one predictor. Our coefficient is 8.9. So that would mean that every day a chicken gained about almost 9 grams. Our p-value is very small, indicating that this seemed to be a good predictor. Our r-squared is almost 0.71, which is not terrible, but it's not great on the other hand. But the p-value for the overall model here is low, indicating that the model fit the data fairly well. We can actually plot the residuals by plotting the model, and we get 4 graphs, which I've put in a 2x2 grid. I have a link in the chapter to a very good explanation from the University of Virginia on these 4 plots, but I'll briefly go through what to look for. Plot 1, residuals versus fitted. We want the red line to be fairly straight, which it is, but we also want the residuals evenly distributed around the line. Again, we notice that funnel shape here. The second plot, the normal QQ, checks if the residuals follow a normal distribution. So you may not be able to see on the video, but there's a very faint dotted line here we see the residuals follow that dotted line in the middle, but at either end it goes off. The third plot is scale location. We want to know if the residuals are spread equally along the ranges. They are not, so the residuals over time vary quite a bit. This is an indication that our data doesn't have the property of homoscedasticity, or the same variance across the residuals. Plot 4 is residuals versus leverage. That helps us find influential cases. We'd want to check any residuals that are listed beyond these Cook's distance dotted lines. And we see some numbers up here indicating some suspicious data points. An outlier is a data point with an unusual y value, and a leverage point is a data point with an unusual x value. I can't read the other number, but it looks like 388 is the index of one potential problem point. So let's just print out from rows 380 to 390 and take a look. 388 does seem large relative to the other chickens. Let's explore that a little further. So I've made a temporary data frame here from the chick weights ordering by weight. This is an R built-in function to sort, and we specify here the column that we're sorting by. So I'm sorting by weight, so I want to look at the end of the data frame to see the heaviest chickens. And I can see that 388 is one of the heavier chickens, but I don't really see any evidence that that's a true outlier. So a true outlier could occur from just data collection errors, someone collecting the wrong information. And if you decide in your data that something is a true outlier and you want to remove it from the data frame before the machine learning, you'd want to document that and also document your justification for doing it. Now let's evaluate on the test set. We're going to use 3 metrics: correlation, MSE, mean squared error, and the root mean squared error. Our correlation is not too bad, 0.82, and our root mean squared error is almost 38, meaning that we're off on average about 38 grams in our prediction of chick weight on the test data. So let's try if adding more predictors gives us better results. Here you see the syntax for adding a predictor. We're going to model weight as a function of both time and diet. And we see here that our R squared went up from about 0.71 to 0.74. The contrast function on diet will tell us about these different levels. So what this means is that the base case is that the chicken was on diet 1. And then we need 3 dummy variables, 3 extra columns here, to indicate that the chicken was on diet 2, 3, or 4. So back up here in our model, the base case is that the chicken was on diet 1. So the coefficients for diet 2, 3, and 4 show the difference for being on those diets compared to diet 1. And we see that diet 3 has the largest coefficient, indicating that diet 3 had a bigger impact on the weight. The ANOVA, analysis of variance function, can help us compare 2 models. So we put in the 2 models and we see them in order. What you want to see is you want to see the residual sum of squared errors go down from one model to the other, and we do see a significant drop. You also want to see a low p-value for the second model or the third. You can compare many models here. And so this is just further indication that model 2 was a better fit than model 1. Let's evaluate on the test set. The correlation is now nearly 0.86, and we can see in our environment comparing the correlation that it has gone up from model 2. And the root mean squared error is now 34. In the previous model it was nearly 38, so that's a significant improvement here. Between the 2 metrics, correlation and mean squared error or root mean squared error, we really prefer the mean squared error metrics. Correlation just tells us that the test data and the predictions are going in the same direction, whereas the mean squared error or root mean squared error quantify the accuracy. A linear model does not have to be a straight line. Next, we try to model the log of the weight as a function of time and diet. Taking the log of the weight will flatten out that funnel shape that we saw earlier. In the third model, we get a much better R-squared score, but let's evaluate on the test set. Our correlation for Model 3 is slightly lower than we had for Model 2, and our root mean squared error is slightly higher. So in order to calculate our metrics here, because we were modeling the log of the weight, I had to do the opposite here for our predictions to put them back in the original units. So the exp function would do the opposite of log. So we can't do an ANOVA comparison with Model 3 because its target is different. Its target is log of weight instead of weight. When we say linear regression, we usually mean a degree 1 model. We just talked about a model that used log, and we can also have higher degree models, polynomial models. Here I have a plot of the cars data set, which measures stopping distance of cars as a function of speed. 4 models were created, representing degree 1, 2, 3, and 4 polynomials. Let's look at the plot. You can see the black line is a straight line, that's a degree 1 polynomial, and it doesn't capture the trends in the data that well. The higher degree models are more complex and may be able to capture trends in the data better. When we run an ANOVA on these 4 models, we see a significant drop in RSS from the straight line, the model 1, to the squared model, and then diminishing returns from then on. So it does seem that the degree 2 model might be better than the degree 1 model. The straight line degree 1 model is probably underfitting the data, and the higher degree models are probably overfitting. In underfitting, the model is too simple to capture trends in the data. In overfitting, the model is too complex and is possibly learning noise in the data. The principle of Occam's razor tells us that when choosing between 2 likely explanations, choose the simpler one. The problem with underfitting is that you don't get a good model of the data. Overfitting won't get a good model either because it won't be able to generalize to new test data. Related concepts are bias and variance. Bias is an algorithm's assumptions about the data. Linear regression has high bias because it's looking for a linear relationship in the data. Variance is an algorithm's sensitivity to small fluctuations in the data. Later we'll see decision trees, which are algorithms with high variance, but also a high degree polynomial has high variance. A term you often hear is the bias-variance tradeoff, which is expressing the idea that algorithms have a tendency towards high bias or high variance. The linear regression algorithm makes a couple of assumptions. First, that the data has a linear shape, and it also makes the additive assumption that each predictor contributes to the model independently of other predictors. That means you may need to remove highly correlated predictors in linear regression in order to get the best model. If 2 predictors are highly correlated, it may be hard for the linear regression algorithm to assign appropriate credit to each predictor. Another problem is that some predictors may have an interaction effect, a synergy between them. For example, imagine a scenario where you're predicting sales from both TV and radio ad budgets. There's likely to be an interaction effect as you hear about the product in 2 different media. Finally, we can have confounding variables, which correlate with both the target and another predictor. An example is modeling weight loss as predicted by activity level, but not considering the fact that age could affect both activity level and weight loss. We can use correlation and pairs to identify correlated predictors. Detecting confounding variables is tougher because you don't know what you don't know. Domain experts can help. Finally, we're going to talk about ridge regression, an advanced linear regression technique. I'm looking at the PDF version. First, we're going to do linear regression predicting ozone from all other columns in the air quality data set. We get an MSE of 442. Ridge regression adds a regularization term to the residual sum of squares. This can correct some of the problems we talked about in linear regression assumptions. The importance of the regularization term is controlled by lambda. If lambda is 0, this is the same as regular linear regression. This is a form of L2 regularization. It squares the magnitude of the coefficients. Each coefficient is squared, then added together to form the L2 term. This is the shrinkage method, which shrinks the coefficients to prevent overfitting. The code in R is shown here. We have to put the data in matrix form, and then function glmnet is used. It does a cross-validation of shrinking the parameters to see what's the best model. The bottom line down here is that our MSE is about 10% lower with this method. You'll notice that the coefficients did shrink in the ridge regression model. I'm showing the end of chapter 5 here. Notice that there was a lot of terminology in this chapter. You'll want to review this. I also have quick reference for new code covered in this chapter, such as how to divide into train and test sets, how to build a linear regression model, predict on the test data, and evaluate. I also have a reference here for the different syntax you can use in building the formula. If you want to use all predictors, that's target tilde dot. If you want to use all predictors except x1, that would be y tilde dot minus x1. Using two predictors, you can use the plus operator. The times operator indicates an interaction effect. Here we're predicting y as a function of x1 and x2 independently, and also as the interaction between x1 and x2. If you want to try just a square model without using the poly function, you can use this notation here. The I is needed to interpret this literally. In the next video, we look at logistic regression, which despite its name doesn't do regression but classification.